Class 10 Science Chapter 4 Carbon and its compounds. Covalent bond, the bond formed by mutual sharing of electron pairs between two atoms in a molecule, is known as covalent bond. Covalent bonding in carbon compounds. The atomic number of carbon is 6 and its electronic configuration is 2, 4. Therefore, needs to gain or lose 4 electrons to attain noble gas configuration. But it is not possible for carbon to form ionic bonds due to the following reasons. It could gain 4 electrons forming C4 cation. But it would be difficult for the nucleus with 6 protons to hold on to 10 electrons. 2. It could lose 4 electrons forming C4 plus cations. But it requires a large amount of energy to remove 4 electrons. Carbon overcomes this problem by sharing its valence electrons with other carbon atoms or with atoms of other elements. Thus, carbon forms covalent bonds. Formation of hydrogen molecule, single bond. The atomic number of hydrogen is 1. Hence it has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So 2 hydrogen atoms share their electrons to form a molecule of hydrogen, H2. Formation of oxygen molecule, double bond. The atomic number of oxygen is 8. So it has 6 electrons in its L shell and it requires 2 more electrons to complete its octet. So each atom of oxygen shares 2 electrons with another atom of oxygen. The 2 electrons contributed by each oxygen atom give rise to a double bond between the 2 atoms. O2. Formation of nitrogen molecule, triple bond. Nitrogen has the atomic number 7. So it has 5 electrons in its L shell and it requires 3 more electrons to complete its octet. So, in order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons that results in a triple bond between the 2 atoms. Formation of methane, CH4. Allotropes of carbon. Different forms of an element that have same chemical properties but different physical properties are known as allotropes. There are 3 allotropes of carbon: diamond, graphite and fullerene. Fullerene. Diamond. In diamond, each carbon atom is bonded to 4 other carbon atoms forming a rigid 3-dimensional structure. It is the hardest substance known. It has high melting point. It is a bad conductor of electricity. It is used in making jewelry. It is also used in cutting and drilling tools. 2. Graphite. Each carbon atom is bonded with other 3 carbon atoms in the same plane forming hexagonal rings. These rings are stacked over each other through weak van der Waals forces. Graphite is also a very good conductor of electricity. It is used as dry lubricant. It is used in making pencil lead. 3. Fullerene. C60, also known as Buckminster fullerene, is the most common form of fullerenes. It has carbon atoms arranged in the shape of a football. It consists of 60 carbon atoms arranged in 12 pentagons and 20 hexagons. Versatile nature of carbon. Carbon is included in formation of a variety of compounds. This is due to the following 2 reasons. Catenation. Carbon has the unique ability to form covalent bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. Carbon exhibits catenation property due to the following reasons. Size of the carbon atom is very small. This enables its nucleus to hold the shared pair of electrons strongly. The carbon-carbon bond is quite strong. 2. Tetravalent nature. Since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of some other monovalent element. Hydrocarbons, compounds of carbon and hydrogen, are known as hydrocarbons. For example, methane, CH4, ethane, C2H6, etc. Saturated hydrocarbons. These hydrocarbons have all carbon-carbon single bonds. These are known as alkanes. General formula is equal to CnH2n plus 2, where N is equal to number of carbon atoms. Unsaturated hydrocarbons. These hydrocarbons have at least one carbon-carbon double or triple bond. Hydrocarbons with carbon-carbon double bond are known as alkenes. General formula is equal to CnH2n. Hydrocarbons with carbon-carbon triple bond are known as alkynes. General formula is equal to CnH2n2. Structural isomers. Isomers. The compounds with the same molecular formula and different physical or chemical properties are known as isomers. Compounds with identical molecular formula but different structures are called structural isomers. Isomers of butane. Isomers of pentane. Isomers of hexane. Hexane isomers. Homologous series. A series of organic compounds having the same functional group and chemical properties and in which the successive members differ by CH2 unit or 14 mass units is known as homologous series. Characteristics of homologous series are times the successive members in homologous series differ by CH2 unit or 14 mass unit. Times all compounds of a homologous series have the same functional group. Times all compounds of homologous series shows similar chemical properties due to the addition of same kind of functional group throughout the chain. For example, homologous series of alkanes is CH4, methane, C2H6, ethane, C3H8, propane, comma. Nomenclature of carbon compounds. 1. Identify the number of carbon atoms in the compound. 2. Functional group is indicated either by prefix or suffix. Functional group suffix alkene ene alkyne yane. Alcohol ol aldehyde al ketone 1 carboxylic acid OIC acid 3. If a suffix is added, then final E is removed from the name. For example, methanol, methane, E is equal to methan plus ol. Chemical properties of carbon compounds. 1. Combustion. Carbon compounds generally burns, oxidize, in air to produce carbon dioxide and water and release heat and light energy. CH4 plus O2 gives CO2 plus H2O plus heat and light. Saturated hydrocarbon burns generally with a blue flame in good supply or air and with a yellow sooty flame in limited supply of air. Unsaturated hydrocarbons are burnt with a sooty flame. Burning of coal and petroleum emits oxides of sulfur and nitrogen which are responsible for acid rain. 2. Oxidation. Alcohols can be converted to carboxylic acids by oxidizing them using alkaline potassium permanganate or acidified potassium dichromate. They add oxygen to the reactant, thus are called oxidizing agents. 3. Addition reaction. Hydrogen is added to unsaturated hydrocarbon in presence of palladium or nickel as catalyst. This process is used in converting vegetable oils into vegetable ghee. Saturated fatty acids are harmful for health, and oils with unsaturated fatty acids should be used for cooking. 4. Substitution reaction in saturated hydrocarbons. The hydrogen attached to carbon can be replaced by another atom or group of atoms in presence of sunlight. CH4 plus Cl2 gives CH3Cl plus HCl. Sunlight required. Important carbon compounds ethanol. Chemical properties of ethanol. C2H5OH reacts with sodium to form sodium ethoxide and hydrogen. C2H5OH on heating with concentrated sulfuric acid at 443 K gets dehydrated to ethene. Uses of ethanol times in preparation of soap, cosmetics and medicines times in alcoholic beverages times as a laboratory reagent ethanoic acid, CH3COOH, or acetic acid. Asterisk pure acetic acid is called glacial acetic acid. Esterification. Carboxylic acids react with alcohols in presence of few drops of concentrated sulfuric acid as catalyst and form sweet-smelling compounds called ester. Hydrolysis. Ester on heating with an acid or a base forms back the original alcohol and carboxylic acid. Alkaline hydrolysis of ester is also called saponification. Soaps and detergents. Soap is the sodium and potassium salt of carboxylic acids with long chain. Soaps are effective with soft water only. They do not form lather with hard water. Detergents are ammonium or sulfonate salts of carboxylic acids with long chain. They are effective with both soft as well as hard water. Soap is constituted of an ionic part which is hydrophilic and a long hydrocarbon chain which is hydrophobic. Structure of the soap molecule is as follows. Cleansing action of soaps. Most dirt is oily in nature and the hydrophobic end of the soap attaches itself with dirt, while the ionic end, which is hydrophilic, is surrounded with water molecules. This results in formation of a radial structure called micelles. Soap molecule thus forms an emulsion. The cloth needs to be mechanically agitated to remove the dirt particles from the cloth. Scum, the magnesium and calcium salts present in hard water react with soap molecule to form insoluble products called scum that obstruct the cleansing action of soap. Detergents are effective with hard water as the detergent molecule does not form insoluble compounds like scum.